First of all, I welcome our today's keynote speakers, Dr. Pankaj Agrawal, on behalf of Catholic Education Society, which is second day of ICTPSC 2025. Welcome Distinguished Principal and member of ICTPSC 2025. Welcome all the deans, head of departments, and faculty members Today's keynote session focuses on enhancing development and energy in composite energy for sustainable development. In today's world, sustainability is no longer a function of independence. Challenges such as climate change, natural resources, and environmental pollution, and rapid industrial growth require innovative and responsible technological solutions. Breakthrough technologies in advanced materials, renewable energy, green manufacturing, clean mobility, and smart systems play a crucial role in achieving sustainable development. To have with us today a distinguished academician, researcher, and academic leader, Professor to facilitate our today's keynote speaker, Dr. Pankaj Agrawal. Thank you, madam. It is my proud privilege to introduce our esteemed keynote speaker, Dr. Pankaj Agrawal. Dr. Pankaj Agrawal is a dedicated academician in mechanical engineering with more than 70 years of work experience. He holds a PhD in mechanical engineering from MIT Overseas University in Pune. He is recognized the PhD under Dr. Babasaheb Ambedkar Technological University, New Delhi, academic research scholars. He has actively contributed to the development of postgraduate programs in design and technical engineering collaborative with NIT 2020. And served as Viewers Manual Institute. The company has held several important academic and administrative responsibilities, including head of department mechanical engineering, PC coordinator, learning capacity manager, and selected extension committee member. He has also played a key role in exponential processes and application activities such as MBA and university level academic work. His core research include application and characterization of composite and composites, new development, machine design, multi-criteria decision making, and intellectual property rights. He has published 57 research papers, including 38 papers in reputed estimated scores, web of science, and prestigious journals. Along with many complex publications, he graduated in 2 process and 4 years. He also served as a leader for reference journals, publisher as journal and science and others. He is a member of the He is actively involved in student development and psychosocial initiatives through the APJ of the Foundation. In the recognition of his contribution to education, he was honored with the prestigious Global Teacher Award of 2021. We are confident that his vast academic experience and research expertise will provide valuable insight into how the opposites characterize sustainable development. In practice, provide proper context allocation to the new use yes. Each of the
Good morning, everyone. Good morning, everyone. Present over here. Everyone, present office. Present of conference. Dr. Vidyanan Sitagar Madam. Report everyone. Conference. Apurva Madam. Industry persons and my dear. It is a great pleasure to stand in front of you with a team of recruit technology for sustainable empowerment, sustainable development. It is really understand for you and government school and organizations. So before starting, I want to one question. You working in my USA, university. University, the United Nations Sustainability Development. These are the 17 goals proposed by the United Nations as well as the member countries. And they are going to achieve these goals in 2030. So the conference and our conference are contributing in terms of to achieve this kind of sustainability. So sustainability conference. So essentially all our technology we know that the limitations and sustainability are not two different stages or different paths. They are working hand in hand. We have the intersection. The breakthrough technologies are not based the cleaner, stable, economic solution. But the solution that redefines the future, that redefines the global sustainability. So, responsible innovation is very important for the global sustainability. Okay, but we will talk about the technology which silently enters every sector of the human life and being human life. And then technology is the look at I will tell about these future technologies. Future technologies because see, the only transformation starts with the material. And nothing runs without the energy. That is why the material science. In the material science, the pressure material as well as the nanocomposition. And after that, there is a efficient energy renewable transformation. So, right, that is why these two sectors are listed here. Now, we know that the solar energy and the wind energy are the three and the clean energy sources. So, setting of these energies are very important for sustainable development. That is why there is a solar photovoltaic 2.4 as well as the clean energy. Then, what is the generation of the energy? So, efficient solar system is also very important. And then, after the transportation of the energy product the smart grids and the Yes. Agricultural country and our GDP is mainly depending upon the agricultural products. This population is very much need to provide. So, the increase agricultural technology are not on the drinking water and the production will be increased. These are some of the district student or country student can work to achieve the global sustainability. 17 SDGs carries a sustainability development goal. The 14 goals are proposed by United Nations and United Nations member countries. It is applicable to all countries. Our performance and the students who are participating in this conference, making contributing to the sustainability goals. What are the contributing for sustainable living? In the context of the competitive world, demand has been increased with great ease over the development of high-speed energy efficient robots, superior engineering systems, and durable materials, particularly that can reduce the sustainability. And use of other material things which include the problem. Everybody the importance of the sustainability. The mobility of opens new doors for finding new materials, new various applications. Basically, they are giving the clear forward. For which applications or which this property to be required, this application of the is the best one. So basically, the non-mobility consists of two things. Non-mobility of the lower of the hybrid non-mobility. Basically, we have to take that one is the annual improvement, instead of the lady, the metal operator, all particles are there. Facility is the machine is the bulk, is the one type of battery. So, we have different types of batteries are there. In the formation of the non-composite is the material stage. So, material system is based on depending upon these two factors. So, which physical properties we need. So, based on that, the materials will change here. Materials, we create the polymer, regular ceramic, regular ceramic, specific properties, and the non-conformal enforcement. So, we require another enforcement. If you are having one of the dimensions in between 0 to 100 nanometers, then it is the low level when out there. Okay. 0 to 100 nanometers. Mechanical, electrical, physical characteristics. Overall so, you have 0.5% addition dramatically changes the movement properties of the planets. So, what is the here? So, this report that the relation between the bodies, the motor performance, the total weakness, the reduction, and improvement indicators. So, small amount of the indicators at the nanoscale is so, this is the basic behind. This is the basic behind the nano. What nano offers sustainability. So, you have to do increasing assessment possible with the component. The line of 50 to 80% of the weight medicine is possible. So, this is the design relation is over. Let's see that movie. Hearing about the single operation. So that he recognized the importance of the fighter jets for the defense application. Okay, now you can imagine how the fighter jet keep the exact rate is increased by 300% at the same time the rate is reduced by 50% over the and then the transformation, bigger transformation takes place in the defense applications. In the fighter jets. The missiles, the cannons, bombs, the family increase. If the family increase, so that will increase. Okay. Similarly, what will happen if the weight reduction in vehicle takes place by 30 to 50%? Automatically, mileage will increase, waste will be required, then automatically cost will increase. So these will increase the number of units from output. Then the value of property. The value of property will improve by 1,000%. The more simple code will be. These are the important movements of the number of property. There are also very like lower consumption of the material and the flexibility there and highway resistance. And these offerings can be considered depending upon the applications or depending upon the targeted problem. So these are some of the factors where the similar problems can work. These offerings are actually contributing the United Nations Sustainable Development Goals such as the climate action, and many more. With the material. Everything is the material. And is the taking behind the amount. Now, basically, depending upon the power, you reach some of the government, you depending upon the power it is, you can post, particular post. And depending upon the matrix material, there are particular vector matrix, mechanical matrix, organic matrix, and carbon. This is the form for a second. When you use the particular form, there is a particular thing. There is a particular form also there, the plate form is also there, upward action. The plate form is from the same, and the so these are the different forms. This is all in form. There is a classification here. There is a particular zero condition to articles. So I can say that action that regulated zero action and it provides a higher base energy. If you provide action of particles, then there is a downstream process and problem. Higher speed ratio and provide the higher range and good electrical and control conductivity. Other side, when you put an action, then place acid form is there for the nanoparticles, then it is the action. Connecting the graphene, it is the last surface area, and it provides the as well as the non-compromising the relationship. The thing is that if the strength is increased, increase, graphene is the material that is the regularity of the material. Then material is available in the hydrometric form. Realization. But at the same time, variable movement as of the force. Now, this problem the process of the middle of the middle of the particles are iron, gold, silver, aluminum, zinc, copper. The middle of the particles are the iron oxide, silicon, aluminum, options are there. Polymer consists of the materials such as thermoplastic, thermoplastic, plastic, and the elastomer. So, you like to lightweight as well as a flexible material, then one can go for the polymer material. The different materials consist of matrix, iron matrix. The signal of the metal and the matrix, then including the highest range and the matrix. Now, they have third into secondary matrix. This is the reason and this is the high the resistance from material. This is the optical secondary aluminum oxide, silicon phase one, no oxides are silicon carbide, silicon dioxide. Now, you need the hydrogen solution. This takes place, and there is a combination. Polymer metal and metal silicon combinations are used. Now, we take our discussion to the next level. One of the nanomaterial that is the graphic, the other metal that is the metal matrix aluminum. To begin our discussion. So, here is the morphology of the graphic instrument. Single layer other is the material. So, in the single layer, it is the observed as a thin sheet. And each placement of metal carbon atoms are placed in a honeycomb structure. When it is manipulated form, it is seen as a black powder, which the plates are in the position of metal or twisted place. This impact on the overall properties because of the carbon atoms that are nanosize. Small change in the graphene can create the better impact on the overall property. Then it is like having the hands. For example, I have taken the graphene with a 4 kilo, aluminum or 6 kilo, 6 kilo. Here we can see 100 kilo, microceptor for 100 kilo, gives a place to the high gives other elements. And when we report aluminum or 6 kilo, 6 kilo, we can see the the form of metal cord, which are uniformly distributed in the so, therefore, application based on the material and that material which are taken. So, there are various cases that cases are listed in the next slide. Now, we have a property material of the graphene with the existing metal material. So, what component can move from the property or the sustainability currently the materials coming from material is the steel. The steel machine is 0.21 like the he gives the paper, which is 0.75 grams per meter square. Now, the it is 0.002 grams per meter square. These will come. So, here you can get one length without
so nice. Nice.
So when you put on the high speed ratio for the so basically the aluminum metal has its characteristic because of clock and the way the aluminum material is the and it is good. So efficiency in the aluminum material is having those strength and low harm. It is so what I mean is of the human life. Here are aspects of critical applications where it is also used in the concept of validity and the use of the aluminum for the automobiles. Here we can see the 12 panels. These are the food associated with these things. Here, these companies, the researcher can target exceptional strength and resilience. These components are power researchers. Children who are brain together, they can so there is a scope for the acceleration in the organization. And you can create these applications, these components using thermal computing. Initially can be achieved with the help of a surfacing method and use of most economy. There are solid-state processing. There the power metallurgy is the most popular. Other methods consist of the power metallurgy, ultrasonic, assisted processing, diffusion bonding, extensive welding, etc. Metallurgy provides the uniform distribution of the nanoparticles in the matrix, but it is quite expensive and like upward of compared with the surfacing method is most commonly and most widely used for the preparation. And any cell can be manufactured with the help of that viscosity method because it is a liquid phase processing. Now, for other metrics like polymer metrics, there is other methods like solution mixing, fluid blending, in situ polymerization, splitting.
Yes.
For the filament mechanics, there is surgery, STS, processing, in situ formation. This is the additive manufacturing. Many researchers are working on the additive manufacturing. Layer by layer, technology itself. So next step after the manufacturing, the next step is the characterization. So for what purpose we have which component we have targeted, which application we have targeted, which application we are manufacturing. So we have characteristics we have achieved. Any calculation techniques are there. So surface topology can be recognized with the help of electron microscopy. Composition of other materials are used to electron microscopy. Microscopy images at the nanoscale, resolution is required. Can be electron microscopy. Nanoparticles shape and size can be determined with electron microscopy. High resolution, electron microscopy. Calculation techniques are there. The crystal particle we can go with the help of X-ray diffraction. Size distribution and atomic scale value of large level space gathering and small level space gathering. Popular processes, other processes are also there. The most important is the material characteristics, mechanical properties. The mechanical properties are available, mechanical properties are there. So every property we can anamorphic, we can take over anamorphic, so there is a delta strength, then hardness spacing will be there, hydroinvitation, hardness is there. The fracture can be checked with the help of hydrocarbon, fracture can be can go for P on this, students functional group, second group, infrared spectroscopy. Spectroscopy composition and oxidation test, that is X-ray photoelectron spectroscopy. There elemental compositions can be checked with the help of energy dispersing X-ray spectroscopy. PDX, PDX or ECS. Those working on electrical field, they can go through this measurement techniques like AC conductivity. There is an electrical conductivity measurement system there. Then electrical constant and electrical loss relaxation period. We can go with the help of a dielectric or spectroscopy. Resistance, there is a 4.4 method. There are other techniques which the electrical product can. for the sake of the component only or not taking for the requirements of the international. These are the results finding which happen personally. And from literature, you can see what how they can ask. The most commonly used materials for aerospace, 281%, resulting in improvement in 283%. Publication also. So basically, here are the multi-wall modules. There is also option model, single wall. TNT and other we have also the Texas and the 127%. So you can see the use of the nanomolecule in the defense, there can be use of the fighter jets, units and vehicles. So nothing is required for high train and weather riding. Also mentioned that levels of storage device, storage device of this as well as the what is specifically behind here? Reduce the fire, 60%. This capacity that can carry the more missiles and other materials, high mobility and the mileage increase and against the for the aircraft usages, being for the thermal cities, the carbon factor of the global seat of the internal rates of the aeroplane. In the aeroplane, every kilogram matters, every gram matters. So, it is very important at the same time improving the station safety is very important. So, this is the sustainability game. This is the aeroplane. This is what now nowadays are. Figure of 20%, there, no meters, in automobiles, what actually automobiles require automobiles due to high competition and different norms like the BS6, the pressure of fuel emission and the higher previously filling in the market. And we need now this new regulation in the now recently we have one with Tata Sierra. So have you seen the pictures of that Tata Sierra? see what the features are here in the tool. Local is Animal is because are just going just to see what features are there in the cars. Yeah. So that is the calculations are taking place in the car. Now, both fundamental students or degree level students, they have calculate these applications like clean mobility, energy storage, then the thermocouple evidence for water purification and the calculation and the thermocouple for the solution also. Nanocube based on polymer composites or the carbon nanotubes are helpful in the achieving the clean mobility. Because composite and graphene based on composites are very problem energy storage, energy storage more efficient. Nanocube cellular and graphene oxide membranes water purification, better other nanocomposites, in the pollution control. These applications are directly linked to the United Nations Sustainable Development Goals. Development Goals target these applications. For the delivery to the environment and safety possibilities. This application development the direct possibilities of the research further. Because these students the components they can use for the flexible or electronics. They can use for the high performance sensor, the energy efficient, experience, electromagnetic intelligence, even activities the identity materials. So here is the developing the ideas of the economy. Sustainability development goals. You can see the sustainability development goal number. No, integrated event students. Integrated event students applications like power calculation, focus on the high energy storage capabilities to provide the high energy density and the thermal stability. The one is component reduce the electric process. Focus the battery and the super capacitor. At the smart grid and the intelligence. It is contributing user to achieve the better future in the our electricity management. Application for the computer science of IT engineer. We can increase the capacity and we can reduce the cycle of that material. Reduce the electronics. Particles are available for these applications. When you are saying about the making the building stronger as well as reliable. Composite is simultaneously transforming building to build the nation and with the better sustainability. If you are looking for the precision of the composite because also they know the potential composite is having. Things in the better in the technology. Getting the non-composite is not just the information. Technologies are not defined by their quality, but by their ability to create a better tomorrow. And sustainability is not the same, but it is the opportunity. I am taking your view. Thank you so much for your patience. These are some of the my professional career achievements. So, actually, in introduction, they have got all these things. Many individuals are there. I don't know there are questions or not. Question from the popular. There is an aluminum and aluminum awards. This was consists of a different aspect, but actually in the today's world they are not satisfying the some needs. So that is why we need of the manufacturing of the nanocomponents. Aluminum as well as aluminum is widely used for steel. Many is the steel critical aluminum. The same time, Fasting if you go for the fasting, it is not you can say. People are actually and now you are going to make it time. So you need to check the evidence because for the moment, see, the beginning that you are practicing management. If you are practicing, then the other management will be different. So you can develop the management account there and there. So they can provide you the instruments and they can get and the percentage also there.
will do will start. Develop. Okay. Obviously, his film. But
alignment and arrangement so that you can improve the size at the nano level. And that's how solidity you're going to make better. Try to make it not something which is available in the nature. Obviously, yes. Some of the, are we there in the nature? And we will see how we go at this thing. They try to look about the costs, see like where is the so, honestly, like a life that I could do in the nature, honestly, this kind of availability is there. It's something I should take rocket science, we are trying to talk about. But then, where you are trying to look for the other applications, you are looking at packaging, you can see like this. Pictures could be very mostly young researchers, you try to like this kind of product. It is something already very so any product what we are trying to look is a polymer and very practice data. So the data that you have to put and and that's how you can generate and make it some personality and lot packaging material like this is the market. Optical materials when you are looking for the polymer and the titanium, the go into more details. Then you will try to see because they are working on a lot of the different kind of, whether it is it's whether mechanical properties and you are trying to do more. These are not different kind of map classes out of it that we have the social requirement. Cities are criteria and good things in the context. That this process is getting something close in houses and that's what people are using. They are already there, which is not doing that. Prices going to give you immediately examples when you try to see it like these are the material which is already that. So let's try to understand some features about this material. Basically, we have to see whether it is existing and the kind of component and the constituents I tried to talk to you it is existing with our layers, layers, series, and how did let me leave that mandatory when you can also try to vary that. Then you do the kind of later. So how you can do it? If you want to kind of look at what the kind of inspires from one to memory, that's how we are trying to so in the beginning, what we are looking at, obviously you are looking and also the classes are as far as they have. So two ways we are looking. And in the cluster, you have the hierarchy cluster, and you have the cluster. Then just identify the same thing. The classes are solid hierarchy, and you have repeatedly interacting. Network and to a network. The two components you already know. But what are the issues we are looking into as the previous hardware? So the goal of GSC is that challenges for the we have to see, but when we are trying to look for a solid measure, most of the class easily matter genius nature variety in terms of the stable citizen they're looking for like in the microphilic obviously there is a challenge. Interaction, how they are interacting with each other, obviously you have certain kind of spectroscopic techniques where we are trying to do. Because of the functionality and obviously we are trying to go from the molecular to nanostructure to the macrostructure and that's how we try to design. Since talking about like what are the approach we are putting to prepare this kind of ideas. Sometimes in the chemistry and then we have the building block. So chemistry you and the examples have been tried to provide activities. So I think these two are very widely has been used. But there is one must say that the as well as we have different product. So we are looking this will change in the property of the precursor. They will be looking for the material. It means mostly people for the in terms of the building blocks, obviously interesting is this treatment about like that. So in terms of the you are actually seeing that how these properties can be developed in terms of the in the space, the cluster material, which is so in the day you like this is again like the basic way you have to understand. And now we need to look at your like what are the techniques we are trying to use for the data. What is what is the complex cost?
Right. So the metals you are trying to look in the form of silica, titania, zirconia, tin, aluminum, and we in our group we have tried all three and it is working quite well. The silica, titania, and zirconia. Still tin and the alumina. We are still looking there actually like how we can try to make mostly when we are trying to go for the membrane kind of research. So again, I'm not going that details, right? In terms of like the alkoxide, when we are looking the alkyl group R, which is like methyl, ethyl, isopropyl, N-propyl, N-butyl. So there is a different kind of alkyl group chains, but don't be afraid actually just to look this kind of metals are the alkyl group. Rather, when we go a little bit more and deeper, then you understand, right? So the basic understanding what we need to be having here to know that when you are trying to go for this the whole process, you are going to look for two ways. Either you can go with the acid catalysis, either you can go for the base catalysis. But the important thing what you must be understanding right here, obviously like I can feel it in the audience, like many people might be working in this sol-gel chemistry, right? Obviously like to make various other kind of compound based on the project what you have thought about. But what is important things what you have to understand is like when you are trying to do the acid catalysis, right? You can see like this is like goes with the linear or the randomly branched polymers. So obviously the structure you can see the way you are going to look there. But when we are trying to go with the base catalyzed reaction, which is second one, then you can say like you are getting like highly branched kind of in a cluster. So again, when we are trying to go for this two processes, based on the application, we try to make it like whether we are going to go with the acid catalyzed reaction or the base catalyzed reaction, right? I hope like you that makes good sense. But let's go a little bit on deeper side, especially on the Sol-Gel process. If you try to look there, so Sol obviously like about this one. Then when you try to see like in the gel where it is condensing and trying to make like building blocks right there, right? And that's how you try to get certain kind of a gel. Obviously, when you apply, like in your household, you have it. You don't realize actually like this is the way you are trying to make the Sol method, or you have the gel how you are trying to prepare there, right? So again, when you try to go next processes, when you have to get the zero gel, you need to just do the solvent evaporation, right? And but again, if you have to retain the same kind of chain, obviously you can look there. If you try to see the sol, when you try to go with the gel, then after when you try to make the solvent evaporation, obviously all the molecules are coming all together. That is zero gel you are looking there. But when you are trying to use the supercritical extraction, obviously you can retain the chain the way you have tried to make the gel, right? So that is called zero gel, right? So there is a different way you try to make it. I'm just trying to give you the idea. We try to go only here Sol-Gel process, right? So that is the way we try to do, and after that we do go for the calcination when we have tried to make certain kind of activated materials based on the good porosity of material. Obviously, I'm not talking today about that one, but again, I'm just trying to give you a little bit idea on that, right? And we can have a little bit on more discussion towards the end when I will try to conclude, right? So here, when we are trying to look at the polymer blending techniques, especially with the Sol-Gel process, you are looking for certain kind of organic material, and then you are looking the inorganic materials, right? So based on that, actually you are going to get in the middle right here. What you are trying to see is called hybrid materials, right? Obviously, with the terminology, you might be quite familiar with that, right? So again, if you have like a source as a silicate layer for the inorganic nylon as a polymer, so obviously you are looking, how you can try to, see, you can easily see from this pictures. I hope like it is quite visible, right? And then how, your polymers, especially the carbon part, like the organic part, and then the metal part, how they are intact to each other, okay? So you can see like polymer modified silicate type of, this layers you can be easily visible, right? And same goes with the silica, with the particles, how it is going to be intact there with the, with the polymer matrix, right? So this is just like a little bit examples what we have. But let's go like little bit very easy way of understand what we are doing. So now this was little bit on the introduction way, just to see to like what are the organic, inorganic hybrid kind of materials. What are the features? What are the properties? What are the generic applications? And then obviously like how we are trying to prepare it, especially with the Sol-Gel process. Obviously, now actually what is sol, what is gel, and obviously like zero gel, aerogel. So there is a the concept what I wanted to see, that is most generic way. And obviously, like when we try to see one type of good example of organic and inorganic hybrid material, obviously, like you are quite familiar now, actually, like when we are looking for the polymer as well as the silica, which is like the polymer as a matrix, and then reinforced material is your silica, right? So silica is form of inorganic, and the polymer is in the form of organic, right? Obviously, you have seen the how the hybrid materials has been formed. So let's talk about today actually like what we are trying to make it, right? you'll be quite amazed to see now the next part of, few slide what we are trying to do, right? So end of the day, our target is actually like to use the waste. You will see different kind of waste we try to do it. Thanks to your organizing team, actually, like who has, organized this, talk to you. I'm feeling like more fortunate to share my views where I can feel like from the audience, like many people's may be more excited to bring more wonderful idea, right? So here, what we are trying to do, we have the source of silica, obviously the precursor we try to talk about, right? We'll see there. And then we have the carbon, right? And what we do actually, like when we go for the carbothermal reduction with the pyrolysis way, then we used to get the silicon carbide, right? That is another vast kind of chemistry we can discuss bit, later stage when we have another kind of, lectures. But here the silicon carbide goes both way, alpha and beta, right? And then alpha is very difficult to, synthesize, but the beta is like, it's more than 560 kind of, electrons are there, right? How it is going to go, because again, you see, this is the one unit cell you are trying to look after, and then then you are going to go like more and more kind of, unit cells. Right there, what is going to form there, right? So what we are trying to do, again, if you try to remember since beginning, that here I try to talk about the silica, right? And then when I go here, the first form of silica, which is the precursor material, what we have selected is called methyl triethoxysilane. We call it MTUS, right? We also take the TUS as you can understand, right? So let's talk about this one. It's called methyl triethoxysilane, right? And then again, the other one is like triethoxysilane. So obviously, like you can easily see, like there is a difference of one methyl group or the other one, right? The ethoxy group, right? So end of the day, when you go for the hydrolysis and polycondenses, remember, I have showed like how this whole process is working. Then we try to make it called polysilane, right? So once we have this polysilane, obviously with the structure what I have showed you before, then obviously I am having the understanding that you still recall, right? So we got the polysilane with this process, and then we need around 40% carbon, which may be coming from the polymers. What we are trying to look at, like we are trying to make certain kind of things, what we call in the beginning of the lecture is called organic, inorganic hybrid materials, right? So we have the TUS, we have the hydrolysis process, then we are trying to make it in the polysilane, which is the component inorganic, and look at the beauty. What we are trying to look actually like that the source of carbon, you can say like the polymer blend, what we are trying to look, it is lignin. Again, I can tell you like we are not trying to talk about more on the craft lignin. I think everybody who's sitting there, you might be making a note on the paper, and paper is the very like I think there is a lot of paper industry. I don't know how many of you have been there, but they have produced a lot actually pulp and paper mill industry where you can get a lot lignin out of it. Okay, how you get it, I'm not going that details. Let me leave that homework to you, but then you can find it. So from pulp and paper mill industry, we try to extract lignin, which is the richest source of carbon, and that's how we make call inorganic, organic hybrid materials. So obviously you can understand these are the inorganic component, and the lignin is the form of organic component. And that's how we are trying to talk about, like, this is the first kind of inorganic, organic hybrid material we made it. But again, the source, which is the waste, right? I will also try to share towards a little bit going more further, what are the waste source we are trying to take about the inorganic component, right? Here, let's see actually in terms of the simple process, you have the polymer, right? we talk about the lignin, again, coming from the pulp and paper mill industry, right? And then we have the polysilane, again, from where this is coming from the precursor material, right? And we make it called organic polymer, inorganic polysilane hybrid materials, right? And then we go for the simple carbothermal reduction. Obviously, the inert atmosphere. I have that story later on. I will say a ritual like one of my students did in the air, and then they says like, there is a ghost because there is nothing left. Obviously, you know the answer, ritual like why, and there was nothing left, right? So once you go for this carbothermal reduction pyrolysis, what we are trying to, get it like we get it silicon carbide, right? Important things what we are trying to look there is kind of some challenges is there in terms of when we get the silicon carbide, there is some amorphous carbon, some unreacted silica, and when we try to do the oxidation, you will see in certain SEM and TEM picture, especially the TEM pictures you will see there. When we try to oxidize, obviously that is how all the amorphous carbon you are, trying to get rid of. Obviously, we are doing with around 700 to 800. Simple Marfil furnace, you can do it, right? And then you get the silicon carbide. Again, this is beta form of silicon carbide, right? And then rest, we are going to get it like unreacted silica out of it, right? So how to get rid of that unreacted silica? Then obviously, like it's very, typical process means you need to be very careful in handling that. We call it like hydrogen fluoride treatment. So again, for that one, you need to have like certain kind of, crucible that is called like a platinum crucible because the HF is highly reactive. So you can damage, certain things. And obviously, it's a precautionary way just to see because it's highly reactive, right? So once you do the HF treatment, that's how you're trying to get the pure silicon carbide. Is it the problem solved? Obviously not, because the big challenge is what we are trying to look there, that we are getting the poor yield. So that is a big challenges we are having. So obviously how to overcome, that is the way actually the group are looking there. And that's how we are trying to do quite a lot of good things right there. How we get it, right? There is a different sources are there. Because of the time actually like what has been provided, I cannot go each and every project. But let me just try to share. This is the very good pictures. You can try to look there, morphological analysis. But again, the source of carbon is very different here. I don't know whether you can try to predict here, but I can just disclose like this is a coal tar pitch based. So coal tar pitch, obviously, it look-wise, nobody want to touch that kind of a research. But we had a project from Ministry of Environment and Forest where we were trying to remove some polycyclic aromatic hydrocarbon. It's called PAH, and then BAP, like benzoapyrene, was the main target. So obviously, like 2 ways we try to remove the BAP, the acceptable label, what the MOEF have defined. And after that, like we were trying to do with the solvent extraction and distillation method. And when we did achieve acceptable level, we tried to see like this is a waste material. So obviously that waste material was nothing with the carbon. So again, as I was trying to say, like we have the precursor material from the inorganic source, which is your MTS or TUS we are looking. And then we got the source of carbon, which is the coal tar pitch. So we combined, we did the pyrolysis. Again, if you try to see from here, the carbothermal reduction, obviously like then we get our silicon carbide. We did characterize, we have to do all the FTIR, Raman. I think if I can be able to show you something I can do, right? And then the second one, if you try to, look here, then we try to go something with the neat polymers. And then obviously, like when we try to go with these pictures, this is all coming from the lignin based, right? So obviously, like you can see the pictures look good. When in South Africa, we were trying to do this research like around close to 16 years back. And the professor who was trying to take this picture, the TEM picture, and then he put his like a profile picture, or he was trying to do like showing to the people like how from the waste you can try to generate like this kind of silicon carbide rod, because it was quite longer. And then important thing is like there was a knot, so it means like all the units maybe they are combining to each other. And then we also received a Y junction, if you try to see from here, and that was also beauty. But important things what you can try to see actually, like what is inside. You can see like from there is a rod, even this side, but there is a gap, something is looking. I don't know whether you can try to predict. Obviously, if I would have been there, just to give this lecture, it would have been more nicer, because I could have just like more interacted with you just to see. But nevertheless, let's try to see like what is there. So what you have seen actually, like from this picture, the previous one, you can see like I'm just trying to talk about here, okay? So you can see actually from there like what the curiosity is coming actually like, and again, whosoever is doing the research, don't be afraid of any kind of negative research. If you get something negative, like if some results is not coming as per your expectation, don't be upset. Try to understand like what may be the problem, because real research is that just to understand like how you can overcome with the problem. And when you try to solve that problem, you may know like there is some serendipity, right? And there is something new discovery, right? There is all of a sudden something can happen, and many kind of discovery, whether it is apple tree story, whether you are looking eureka kind of story, many ways actually you can see even the magnetic field, right? So there is like always happens something where you can see actually like uh, you can try to predict. So here you see the middle one is what? Silicon carbide. And the outer one, if you try to see from here, I'm trying to talk about this is the middle one and this is the outer one. So obviously like from there you can see like it's a silica, right? So, and you can see from the picture itself that how it is looking like, right? And then again, when we did the HF treatment, obviously this pictures has been taken before we did the HF treatment, right? And as I was trying to promise, like how we try to characterize, we have the XRD, right? How the material is going to be looking like, either crystalline or amorphous. Obviously, with the material, actually like what is going to be, right? And then when you do the FTIR and the Raman spectroscopy, that's how you try to see actually like how the silica SiOSi or O silica oxygen bond is going there. And we are looking there, and obviously like it's a good calibrated FTIR instrument, so that you can see actually like you are getting quite a neat picture. So this is not like fabricated or something. This picture is there, and obviously like this paper has been published long back. It's good in citation as well, so you can see, and then you can try to follow the kind of work what I am trying to share with you, right? So what we are looking there actually in terms of future materials, what we are looking there, that we are trying to develop this kind of silicon carbide material right here, but we also have some unreacted kind of silica right here. So end of the day, when we are trying to look this kind of aspect, we are also trying to find it out, like how it is going to be like more helping when we are trying to design a new kind of projects, a newer kind of perspectives what we are looking there, right? And that's how it is coming like the future project is coming like once you encapsulate with a quantum dot, obviously you can. And those people who is working, I'll be waiting actually certain question answers to like when I try to finish. And then we can do the encapsulation of enzyme, DNA, and the metal complexes. And obviously, like I'm talking about like when we have not done the, um, the HF treatment, like it is still with the silica. Why we want to still keep it there? Obviously, you can try to understand it like this is certain kind of obvious reasons are there, right? And that obvious reason I can try to see with the functionalization, and obviously you can try to understand, right? But if not, we will interact and we can try to say like how it is going to there. But this can be, the encapsulation is going to help in terms of like making a good hybrid system. What we are trying to look at like a very good solution in the near future, right? So the end of the day, what I try to share with you, like the beauty about today's talk is like, it's just like very simple material. You are making hybrid material, right? But the source that we are trying to talk about is called waste, right? And in terms of the waste, again, for some people it can be waste. For us, it's like a gold, right? I'm not talking about gold nanoparticle or the gold material right here, but I'm just trying to say like what may be the waste for some other people. This can be a very good for us, right? And the one resource what I try to talk about is called the lignin, right? And that one, it is coming from the paper mill industry, and obviously like how you are trying to look. So end of the day, what I have not said in the beginning is like what I'm leading the research lab, which is called Sustainable Materials Laboratory, SML, right? So there we have the concept very easy for people to follow us and do something like what kind of research what we are trying to do. It should have a kind of a zero waste, and also whether the material is sustainable. So that is the whole concept is there. So end of the day, when you are trying to look for this lignin, which is coming from pulp and paper, but besides that, we have other kind of raw material. And from this slide, you can see it can be from the wood, wheat straw, bamboo. Obviously, you can look for the bamboo shoot as well, right? Which is highly in conducting nature. Then you have the sugarcane bagasse, a reed, and the waste paper, right? So that is the way we are trying to look. And why we are looking there? Because this has around 78% of organic and 22% of inorganic component. And when we are looking in terms of like their, some graphics, the analytics, the data, you can try to see it like it is like widely produced, and how we are trying to make it. Just for example, if you try to look for the lignocellulosic substance, especially with the pulp and paper mill, right? So you can see like daily you have like 200 cubic meter per tons annually you are producing around 40,000 million cubic meter. So the idea is like mostly it is coming from the paper making, which is then you are trying to look for the papers, and then you are producing a lot of effluent, which is called black liquor. And we are trying to extract, very simple process we do, just to extract the lignin out of it from the black liquor. So that is a little bit story from your side, so you can understand. So in terms of like why we are trying to target these kind of things, we need to look there. That is the real science, why this faculty development program has been, organized for you to get more ideas, more, energetic or motivated to see like whether you can participate to do a very good work, what is just lying in your corner, right? So in this one, when we are trying to look at like why we are trying to talk about this pulp and paper mill wastewater, right? So if you try to see there, this pictures is quite, looking good, no? Obviously, you can see this is the sunlight where this, the lignins are enriched. What is there? Are they trying to penetrate? Obviously, it cannot go, because they try to protect. Okay, And why it is protecting, obviously you can Google it today or maybe YouTube, and you can try to see it. You like they just stop on the surface. And then if it is happening like that, what is happening? It is reducing the oxygen, reduction of photosynthesis. And then obviously like it can make like different kind of, harmful byproducts like dioxins, another kind of research we can try to do. But I'm just trying to see. And then obviously the aquatic life is already getting affected. Another kind of, parameters when we try to look for the EPA, which is Environmental Protection Agency, where you're looking for the turbidity. Acceptable is around 75, but we are getting around 750 TNTU, right? pH 6 to 9, usually like slightly 7. You have to go, but it is ranging more. Then the TDS, the total dissolved solids, you are looking around 1500 acceptable, but obviously you can see the data, the BOD, the COD, the total suspended solids, obviously you can look. And what I'm trying to talk about, the gentleman, are the kind of compound we call it lignin, right? So end of the day, it will like there is a process like a simple sedimentation, coagulation, flocculation process, how you try to do, and we extract. And then you can also try to do it via the membrane process, the ozonation process, actually just to make sure actually like what are the real current practices people are trying to follow for this kind of effluent treatment, right? And what we have done so far, actually, like we have taken this lignin. Again, I'm not going more on details, actually, like how we try to take it. But when we try to take it out, then we are trying to look actually like how we can make different kind of composite materials, right? So the one of the project what we have done actually like this was a little bit battle actually in the beginning, but we got this paper and um, then we have made something called like a composite material, and we try to look actually what are the material properties, especially the strength and the toughness, how it is going to form there. And then the other one what I just now share with you actually like just to make the silicon carbide, right? So that's what we did it. And then we did not stop right there. As I told you, like we were working not only with the silicon carbide, but we were working with the other metals like titanium and zirconia as well. And we tried to make it like titanium carbide. So obviously the process is the similar. We took from the pulp and paper mill industry, we extracted the black liquor, and then we got the lignin. Then we have the solution method, and then we got the lignin, polymer blend, and then we incorporated the titanium. Obviously, we are looking for the anatase phase here. And then obviously like we make the lignin, ketosane titanium nanocomposite right here. But I think if you have to follow, these are the papers like journal we are looking, International Journal of Biological Macromolecules, which has been published in 2018. Quite good citation is there actually. So obviously you can follow, and the pictures are looking quite amazing there. Okay. So that is the way actually like we have not only made like the silicon carbide, but we also try to make the titanium carbide out of it. And the process is very simple. Those who want to do actually this kind of research, more than welcome, to join our group and do certain kind of things. It's quite easy process. I will try to explain in the end when anybody will be interested. As for the faculty experience, you want to come visit us like for 3 to 6 months. There is some processes to follow. Even from the student side, like whether you want to come as a full-time master's or PhD, and then obviously like you can only if you only want to visit for a certain period of time, there is kind of things so you can get good experience, not only with the research but also from the nearby places as well, right? So the whole concept is coming to our side, if you like, what we try to do based on our research, if you like, how we can continue building this kind of sustainable concept out of it, right? So obviously, like if you try to look there, this is the sustainable possibilities what we have proposed there, and there you are having like reutilization of water. Obviously, like from the black liquor, you are trying to, take it out, and then you can also try to take out certain kind of inorganic, the metals out of it, and then obviously like that is where you can try to sure it, you like how you can have the clean water reutilization, right? So there is a way actually we try to do a lot of adsorption, the membrane chemistry. I'm not talking today on that actually, and that is where we try to make this sustainable concept, especially for the safe and clean drinking water, right? And then in terms of the industrial application, if you're trying to look like we have the chemicals like dispersant, then we have the blinder, the polymers, then obviously like when you are looking for others like cement and battery, again with the cement, there is another kind of research what we have done. We'll say maybe another time. Then we for the agricultural is controlled release of the pesticide and herbicide, which is a bigger challenge is coming at this moment. Then the biofuel, we have the diesel, syngas, hydrogen, the chars, like to produce the activated carbons. So we are trying to bring a lot of things, but that is again coming from the industrial application of the lignin only, right? So there is a lot of way we could try to do, and then again, like when you have to produce that much of lignin, how you can try to reuse it. So basically like reusing in terms of like if you try to the electrodes, you can have the hydrogens production. Obviously like that is another project we are trying to do. I'm just trying to say a few things like what maybe quite showing a good interest to you, right? And then obviously the recovery of the inorganics, obviously you can see from this picture like it's quite easy way what we are trying to do, but I'm just trying to make certain kind of ideas to your mind that you like it can be coming there. But we are also having like one project with the sensing application of the contaminants in the water, how we can do it like different kind of dyes. We try to see like in this one we have highlighted about the naphthyl blue black NBB, but there is other kind of the organic dyes we try to do, right? So there is a lot of way we have a good hypothesis actually like what are the sustainable possibilities it can be there, right? So the important things what I have said in the beginning, that it's not only like you have seen the one part. Again, I'm not going to take a lot of time, maybe another 5 to 10 minutes. Let me just see if that will be allowed as well. So you can see like from there, you have seen the carbon source as a waste material, but here is the way actually what we are trying to take the first slide, especially like the silica source. So in you perhaps be knowing that I'm in Cape Town, and I'll show you one picture maybe towards the end. Actually, you will see like it is quite beautiful city, and people's like visitors, especially where the wineries is quite famous. Even the great Napoleon used to buy his own wines from this side. I'm talking about 1785, that kind of time, right? Constancia is the fruit is the right place, if you try to visit there. So end of the day, when we are trying to look about the wine glasses, that is the one, like once you drink it, that is the source of silica we are looking there. So obviously like the inorganic source as well, you are looking from the waste. Obviously people throw it, but we try to use that as a source of silica just to make certain kind of silicon carbide materials. That is one thing. But here is like in this project, what we try to see actually like we have the glass from the waste, and then obviously like we are simply trying to make the electroplating industries for the wastewater treatment. Obviously, like we try to extract the dyes, and then we try to put it like nice colored kind of glasses. That is another project we can try to share one of the time actually, right? And then obviously like what I have said in the beginning about the biochars, and I think you still remember the wood plates, and that's how we go with the simple sol-gel method, carbothermal reduction, and we try to make the silicon carbide. And then again, titanium carbide, obviously you have seen there. Another things what we try to do actually, like we try to find a substitution about the cement. Obviously, you know that cement has one of the very good kind of uh, compound which is called pozzolan, and that one how you can try to replace, and we try to make that one possible by using the fly ash, which is a waste material from the power industry, and then we combine with the cyclodextrin and as a inclusion complex for the cement production, right? So that is the way we are trying to also make it there. So end of the day, what is whole approach of today's sharing, is like we are trying to make it certain kind of material coming from the waste source, and we are trying to make it the advanced materials. Those people who is not aware, obviously, especially with silicon carbide, is like highly stable, thermally stable material, and people are using a lot for the defense kind of area, right? And some people who's making kind of mesosporous material, they're also using a lot with the silicon, silica based actually materials right there. So we have one academy we have established side by side, which is called Academy of Nanotechnology and Wastewater Innovation. I think like a little bit, I want to give you the idea. So where the academics, the educationalists like you, industry partner, like they are few already doing. Environmental bodies like within South Africa and other side, they are quite involved there. And the mission is very simple: networking, how we can try to turn the materials in terms of the product development or having some sustainable solutions, promote recycle, reuse kind of and reduce kind of material, and develop a sustainable environment for future generation. So that is the mission we have, and the vision is very simple: how we can innovative attitude we can have, the conceptual knowledge we can try to bring it there, and how you can learn something what you are thinking beyond the limit, right? And then securing experience, knowledge, and skills. Activities we are trying to do a lot of nanotechnology or wastewater treatment or the waste valorization kind of courses, the science engagement we are trying to do it there, and organizing a lot of science advancement. So I think those people who may be like interested, you can try to see, like, because we have very good expertise in terms of like nanomaterials development. If you try to see variety of nanomaterials we are trying to develop, few things what I have shared, it was just because of the time constraint I cannot go all of them, but we are focused mainly on the membrane photocatalysis, adsorption. For the energy, we have like the hydrogen generations, and obviously like with the waste valorization I have shared today based on the organic and organic hybrid materials. And I just told you like we are trying to do with the industrial partnership, academic research, product development, and outsourcing of the knowledge. And most welcome actually you can do. So you can follow us, you can get back, and you can connect wherever you can. Important thing is like we also have a very good student chapter in the form of IEEE, which is Institute of Electronics and Electrical Engineers. And then I am heading the Nanotechnology Council South Africa chapter. So it's like if you can connect, you can be able to do a lot of things with us. So this is almost another 3-4 minutes just to finish my talk. Is like beautiful city. I think you are now should be quite happy, or you have listened certain thing called research, but this is called like something like you can try to come. This is a Table Mountain. You can see it's looking like a table. You might have not seen actually any kind of mountain which is going to look like a table, right? So that is the beauty about this Table Mountain, and city is very beautiful. And you can see these pictures with the stadiums and everything, and people really come to enjoy. And what you can enjoy, whether you want to have the African safari, walking with the lions, playing with the cubs, obviously like that is the way actually you can try to have the good life. This one is like the wineries I was trying to talk about, like, they are quite popular in terms of like producing great kind of, good wines. And here, like, there is a kind of like every 200, 300 meter, there is a, wineries. Even like when I am sitting here, it's around 500 meter, there is some wineries are there. And then you can go there, have different kind of wine tasting there. And I think you can really enjoy, right? But I love this snorkeling. Sometimes I go little bit cold water, but still, like for the good life, you can just try to, enjoy there. This is one of the hobby I have not yet done so far. I have to do actually, and that I have my booking. Let's hope actually in coming days I am going to do. It's called skydiving. That is my to-do list. But this is the way people enjoy this side. And this is the wine I was trying to talk about, actually, like what used to be, like produce very old one, and it's quite popular. So I just took the picture. Obviously, it can be a little bit vague, but still you can see there. With that note, I have to acknowledge I have forgotten certain people just to put it there in the list, but I think like there will be a lot coming, even from your side as well. And with that note, I have to say thank you, and I want to welcome questions and queries from your side. Thank you.
Thank you, sir. Thank you. Any question? Questions? Chemistry people? Huh? No questions.
Okay, I'm listening.
Yeah. I have a question, sir. Will you
Please
open
go
your,
ahead.
slide number 30?
Yeah.
Slide number 30, please.
You tell me where to stop, right?
Next. Next, please. No, you are going back, I think.
This
Slide
one?
number 30. Slide number 30. Last third or last fourth slide was there.
Okay, just hold on.
Related to coagulation.
You mean this one?
No, next. No, it is not. Separation of organic and inorganic components by using coagulation. That I want to request you to elaborate little. No, this earlier you have presented. I'm not understanding whether you are going ahead or back.
Okay. No, you can see actually from this side, and you can tell me, is it this one you are trying to look?
Down, sir. Next.
This is the coagulation, right?
Next one. Next.
This one?
Next. This one.
Okay.
Yeah. Here you have mentioned now that black liquor by using coagulation, separating the organics and inorganics. Which method can be used for the separation, or directly whether that method, coagulation method, is directly separating or only recovering the inorganic?
The coagulation method is just to get the lignin out of it, right? So all are like a different approaches. I try to put it here. So here from the black liquor, we are trying to use the coagulation method, and from there we are extracting the lignin. And obviously, like when you are looking for the lignin, then you are looking for the making the silicon carbide out of it, right? But when we are trying to look for the like little bit more further approach, you are trying to look like you can take the lignin out of it, you can make a composite, right? And that's how you could try to remove the inorganic, which may be your chromium, arsenic, lead, so those kind of 5 metals what we try to target, like cadmium, So that is not like itself with the lignin, it is possible, but we try to make it like a more composite, and that's how we try to do. So what I have presented in this one is like it's a very very narrative, very small, precise way I
Yeah, just
presented. But there
idea,
is
just idea you have.
just the idea, right? Yeah,
Yeah. Yeah,
great.
thank you, sir. And thank you for showing the presenting the opportunity for collaborations and
Yeah.
creating the chapter also.
I think that will be quite nice, and that is why I tried to
Will you
go
please
like
mail
more.
me that? Will you please mail me that?
Yeah, definitely, sure.
So we can connect through mail and then we can decide. And,
Definitely.
Yeah, we are connecting after a long time. Thank you.
You're
now
more than welcome to connect anytime, right?
Yeah, thank you. And now I request Shinde sir to present the vote of thanks of this session.
Yeah.
Good afternoon, all. I, Dr. S.M. Shinde, I would like to propose a word of thanks. Thank you, sir, for delivering the keynote address on organic and inorganic hybrid materials. I sincerely appreciate your valuable insights and time shared with us, along with your research areas. You have taken us to African safari and into the research field. I sincerely appreciate your valuable insights and time shared with us. And also, I'm equally thankful to all participants, researchers, faculty members, and students for silently listening the session. Thank you once again. Thank all.
Thank you, sir. Most welcome anytime.
Okay, thank you, sir.
Thank you.